So, welcome back to my lectures on groups, rings, and fields. Our next topic is on group presentations. Group presentations. Group presentation is another way of expressing or defining a group as free as possible, meaning we are trying to find ways to derive a group from a free group. And we have done this earlier when we try to identify a free abelian group from a free group. So let us start with that known example. What we have done earlier is that if A is a set and f of A is the free group generated by the elements from A, then FA, the factor group FA over C, is a free abelian group. F of A is not abelian, but this factor group is an abelian, where C is the commutator group of f of A. See, the commutator group is a normal subgroup of f of A, and that is the reason why we could take the factor group or quotient group. We are going to generalize this for the group presentations. What we are doing here is actually taking the quotient of a group over a subgroup. So this subgroup is actually a subset of f of A, right? Meaning we are placing some conditions or criteria on the elements of f of A to generate C. And that condition is actually AB, A inverse, B inverse is equal to 1. Because the commutator subgroup of f of A, well, I'm going to assume that A contains only 2 elements. So just for the sake of simplicity, I'm going to take 2. So this C is generated by the elements of the form AB, A inverse, B inverse, where A and B belongs to f of A. In this case, because it is generated by these 2 elements, I can write it like this. So this is actually, the C is actually generated by elements of A, B, A inverse, B inverse. Right? Where A and B belongs to f of A. When we take the factor group here, the identity of the factor group is this commutator subgroup. That is, C is the identity of f of A over C. So in the quotient group, all the elements, the the group containing all the elements of C, and which is C itself, is the identity. So these elements, the elements of this group, this factor group, satisfies this condition, because whenever there is an element of this form, that is an element in C. So, in other words, f of A over C contains all the elements of f of A with the condition A inverse B inverse equal to 1. Actually, this is isomorphic to the group containing this, because this actually contains all the cosets, but that will be isomorphic to a group with this. Okay, so what we are doing here is that we are enforcing a condition on the elements of f of A to form a normal subgroup and take the quotient of that. And that is exactly what is happening here. So if A is equal to AB, then if you put the condition A inverse B inverse equal to 1 on f of A, meaning whenever there is an element like this, that will be replaced by 1. Then we will get a subgroup of this. We'll get a subgroup of this, and that will be isomorphic to f of A. Not a subgroup actually, because the binary operation will be different. So f of A over C will be isomorphic to that group. This is the idea behind the group presentation. Instead of a specific condition like this, we are going to take any condition, any condition on f of A. See, in this condition, A inverse B inverse, A inverse B inverse is a member of f of A. So the condition always would look like an element from here equal to 1. And that is where we are going to. That is a generalized version of this construction. Okay? So what we have done so far is we have a set A, 2 elements, and we constructed the free group generated by this, and we also constructed the commutator subgroup of f of A, and that is basically C is equal to the subgroup generated by A inverse B inverse. Okay, then what we did is f of A over C, took the quotient group of f of A over C, and that we found that this is a free abelian group. Okay, so our aim is to get a group isomorphic to this from a free group. So we are actually deriving this group from f of A. And how did we do this? We created a subgroup, a normal subgroup of this, and took the quotient. That is how the free abelian group is formed. Okay? And when we created this normal subgroup, what we did here is that we took elements from f of A that is generated by this. Okay, and this element A inverse B inverse is actually belongs to f of A. Okay, this is the idea we are going to use to generalize to get the group presentations. So so what we are doing here is actually wherever you pick up the elements from f of A, and wherever you find a combination like this, replace that with 1. Then we get an element in here. We'll take an example here. Let us say B cube A inverse B inverse A to the power of 8. This definitely belongs to f of A. But when it comes to this group, this will be collapsed to 1. So it will be B cube A to the power of 8. This also belongs to f of A, but in f of A, this element is different from this element. Okay, this belongs to our G, and it is actually identified as B cube A8 plus C in f of A over C. So the idea is to enforce some conditions on f of A to get the new group. So that is the idea here. So what we'll do here is, to generalize this concept, here we have only one condition, but we can have as many conditions as you want. So what we'll do is, Ri belongs to f of A for some I belongs to for some index set. So this is actually Ri. Ri belongs to, we'll say like this. One of them is our A inverse B inverse. Okay. So when you say like this, what it means is, whenever you have an element in here where you have a combination like this, replace that with 1. So we are going to create a subgroup just like this. The way we are going to construct the group is that whenever you get a value of 1 while replacing each Ri to 1, then that element belongs to the group. So R is a group or is a subgroup of f of A where the value where the elements are reduced using Ri. Well, we still have to prove that that is a subgroup. For example, let us take elements like xi's, okay, and what we will do is xi times rj times xi inverse. What is this? This is actually 1. This, if rj comes from here, this is actually 1. So this is equal to xi inverse, xi times xi inverse, and that is equal to 1. So if it is equal to 1, that belongs to R. For example, here, if you say B cube AB A inverse B inverse B minus 3, this will belong to R because this is actually 1. So this is actually 1. Not when you compute, this will be 1. So this, the whole expression is 1. But actually in f of A, B cube AB A inverse B minus 3 is not equal to 1 in f of A. This is a different group we are constructing it. It's a subgroup of f of A. They are not equal, but this element is in R. Now, R is a claim. The claim is R is a normal subgroup. That is very clear because when you compute the elements of R, that is equal to 1. So if you take a Y times an element in R is equal to, this is actually when you compute this will be 1, equal to R times Y. That means Y of R is equal to R of Y, implies R is normal. So this is equivalent to our C. Okay, so this each of Ri are called relations, and relators, and Ri is equal to 1 is called relations, and any element of R formed like this is called consequence. For example, here one consequence of this relation is going to be if you take pi I is equal to 1 to, let's say, n, xi r j or xi to the power of ni, rij to the power of let us say ji, and n xi to the power of minus ni. This is actually an element of R. So this is a consequence of finite product of the powers of the relators of this form also belongs to R, because this, when you compute, this will be 1. So if this is 1, this will automatically becomes 1. So it actually belongs to R. So let us formally define a group presentation. Definition: let A be a set and f of A is the free group generated by A. Let Ri belongs to f of A and R be the smallest subgroup, smallest normal subgroup generated by, smallest subgroup containing Ri, I belongs to index set. Then an isomorphism phi from f of A to R onto G is a presentation of G. See, this G is not a subgroup of f of A. We are just having a isomorphism from the quotient group to this. For example, in our case, in the earlier case, f of A over C is isomorphic to, here it will be C cross C if A is equal to AB, contains 2 elements. So this is our G. This is actually our free abelian group. Okay. Now, then Ri's are called relatives. Ri is equal to 1 is called relation, and any element in R is called a consequence. And then A is finite and Ri is finite, then it is a finite group presentation. And that is a formal definition of group presentation. We'll do some examples and problems. Now let us do a very simple example. Let us find out group presentations of Z4 with one generator and two generators. By the way, when we write the group presentations, what we do is it's like these are all, we'll write it as relators first, then column, then we will write the conditions like Ri to the power of 5. Just Ri to the power of 5 is enough. This means that Ri 5 is equal to 1. You can write it as Ri to the power of 5 is equal to 1 or just Ri. So we can also write like R1, R2, R cube, R square, or R1 cube, R2 square. This means that R1 square is equal to 1, R1 cube is equal to 1, and R2 square is equal to 1. So here, let us start with one generator. Let A is equal to 1 generator. So FA is going to be 1 A square dash dash A to the power of minus 1, A to the power of minus 2 dash dash. So this is FA. This is actually cyclic, and because there is only one generator. We want to pick elements from here to form a group isomorphic to this. So this should contain, when we pick up the elements from here, should contain only 4 elements. And how do we do that? See, if you take a condition like this, A to the power of 4 is equal to 1, or either you can write it as A4. Both are identical. Okay, this is a representation I am suggesting. See what happens here. See, if A to the power of 4 is equal to 1, that implies A square times A square is equal to 1, and that implies A square is equal to A to the power of minus 2, and that implies A is equal to minus 1. Because of this, any element from here with a negative exponent can be written as A. So there is nothing here. If you enforce this condition, A4 is equal to 1, we don't have any elements here. This is all eliminated. See, A square, A to the power minus 2 is actually A square. It's already there. So when you enforce this condition, then we don't have negative exponents. Now, what are the other? So how do you really find a group here? The elements from f of A will be 1 A square, A cube. There is nothing on the left hand side because it's all gone. A to the power of 4 will be 1. So that is it. A to the power of 5 is A. A to the power of 6 is equal to A square, etc. So, and that is actually isomorphic to Z4. So one presentation of Z4 with a single generator is this. Let us find another one with two generators. So let A is equal to A comma B, and f of AB is the free group. So basically this is actually f of A will contain elements like this, and also along with this you will have a product of B also. So here what we will do is, the condition is A comma B, A to the power of 4 definitely is equal to 1. Then what we do is, B is equal to A square, because we need to eliminate B. What happens here? With the earlier argument, you don't have any exponents of negative exponents on A or B in f of this and in the free group. So you don't have A to the power of minus 1, A to the power of minus 2, etc. And B also is like that, because B is equal to A square. Now we'll have 1A square A cube with this condition. Now if you have if you have a B, that is automatically converted to A square, which is already there. Then if you have an AB square, what happens? That is equal to A times B square is A, that is A square. So with this condition, you don't have any elements from f of the factor group which contains B, because everywhere there is a B, that is replaced by A square, and everywhere there is a with an exponent higher than 3, it will be changed to either 1, 2 or 3. So this is another presentation of Z4 with two elements, two generators. Here with one generator, here with two generators.